The morning of October 12, 1942, Hauptmann Friedrich Lang stood in a muddy field outside Lille, France, staring at something that shouldn't exist. The B-24 Liberator lay crumpled across 200 yards of farmland, its olive-drab paint scorched black in places where fuel fires had burned themselves out. Lang commanded the Technical Intelligence Section for Luftwaffe 3, and his job was to extract every piece of useful information from downed Allied aircraft before they were scrapped for metal. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. He'd examined dozens of wrecks, British Wellingtons, American B-17 seconds, even a few Soviet bombers that had strayed too far west. But this Liberator presented something different. The aircraft had been intercepted at 27,000 feet by fighters from Jagdgeschwader. Two took catastrophic damage to two engines and somehow glided 20 miles before the crew bellied it into French countryside. 3 crewmen were dead, 6 captured, and the aircraft was surprisingly intact for something that had fallen from 5 miles up. Lang walked the perimeter first, noting the battle damage. 20mm cannon strikes in the wings, the No. 3 engine completely destroyed, No. 4 feathered and locked. Standard kill pattern for an experienced Luftwaffe pilot. What caught his attention was the cockpit area. He climbed through the twisted nose section, past the bombardier's station, and into the flight deck where morning light filtered through shattered plexiglass. The instrument panel was a mess, but Lang wasn't interested in the gauges. He was looking at the crew positions, specifically at what the men had been breathing through at 27,000 feet. Rubber hoses snaked from overhead connections to oxygen masks that still hung from their mounts. Lang traced one hose back to its source and found himself staring at a system that made absolutely no sense according to everything German aviation medicine understood about high-altitude flight. The oxygen regulators were sophisticated, far more advanced than anything installed in Luftwaffe bombers. Each crew position had individual flow controls and pressure gauges. The main oxygen bottles, 4 of them, were massive cylinders mounted in the fuselage, each stamped with pressure ratings that suggested they held oxygen at 3,000 pounds per square inch. Lang did the mental arithmetic and felt something shift in his understanding of what the Americans were actually doing. At that pressure, with that many bottles, a B-24 could supply 10 crew members with oxygen for 6, maybe 7 hours at altitudes above 25,000 feet. That wasn't emergency equipment for brief climbs through dangerous altitude. That was a system designed for sustained operations in the stratosphere. The Americans weren't just claiming they bombed from 28,000 feet. They were engineering their aircraft specifically to live up there for the entire mission duration. The implications spread through Lang's mind like cracks in ice. If the Americans could actually operate at those altitudes routinely, not just in short bursts but for hours at a time, then every tactical assumption the Luftwaffe had made about defending occupied Europe was wrong. German fighters were optimized for combat between 10,000 and 20,000 feet. Above 25,000, performance degraded rapidly. Engines lost power in the thin air, pilots struggled with cold and hypoxia, and engagement times were measured in minutes before you had to descend or black out. But if American bombers could park themselves at 28,000 feet and stay there for the entire mission, they were operating in an altitude band where the Luftwaffe simply couldn't reach them effectively. It wasn't a matter of courage or skill. It was physics and engineering, and the evidence was lying in pieces across this French field. Lang requisitioned a truck and ordered his technical team to strip every oxygen-related component from the B-24. Bottles, regulators, masks, hoses, pressure gauges, even the instruction placards stenciled on the bulkheads. He wanted everything shipped back to the Luftwaffe testing facility at Rechlin for detailed analysis. By sunset that day, components from the Liberator were packed in wooden crates and heading east on a supply train. What they would reveal over the next 3 weeks would force a complete reassessment of German defensive strategy. Understanding why the Germans were so skeptical requires going back to the very concept of strategic bombing at extreme altitude. The idea of flying heavy bombers above 25,000 feet wasn't new in 1942. Theorists had been proposing it since the early 1930s. The advantages were obvious. At those heights, you were above most anti-aircraft fire, above bad weather, and theoretically beyond the ceiling of most interceptor fighters. The problem was that nobody had actually proven you could do it operationally, day after day, with hundreds of aircraft. The human body doesn't function well at 28,000 feet. At that altitude, atmospheric pressure is roughly 1/3 of sea level pressure. Without supplemental oxygen, a person loses consciousness in under 2 minutes. Brain damage follows quickly. Even with pure oxygen, you're operating at the edge of human physiological limits. Cold becomes a serious threat. Outside air temperature at altitude runs -40 to -50 degrees Fahrenheit. Frostbite can occur in seconds if you're exposed to slipstream through a broken window or damaged turret. The Luftwaffe's own experience with high-altitude operations was limited and problematic. German bombers like the Heinkel He 111 and Junkers Ju-88 were designed for medium-altitude work, typically 12,000 to 18,000 feet. They carried basic oxygen equipment, compressed gas bottles with simple delivery masks. But these systems were meant for occasional use during climbs or brief high-altitude transits. Crews reported constant problems. Regulators froze, hoses kinked, masks leaked, and after 2 hours at altitude, even healthy young pilots experienced crushing fatigue and impaired judgment. German engineers understood the theoretical solutions. You needed high-capacity oxygen storage, pressure demand regulators that automatically adjusted flow based on altitude, heated delivery systems to prevent freezing, and backup redundancy throughout. But building such systems required manufacturing precision, exotic materials, and weight penalties that seemed prohibitive. A complete high-altitude oxygen system added several hundred pounds to an aircraft's empty weight, reduced bomb load accordingly, and required extensive maintenance between missions. More importantly, the Luftwaffe's operational doctrine didn't emphasize high-altitude bombing. Their experience in Spain during the late 1930s and in Poland, France, and the early Soviet campaigns focused on tactical bombing in support of ground forces. That meant medium altitudes where you could actually see your targets and coordinate with advancing armies. The idea of flying blind above 25,000 feet, dropping bombs through clouds onto targets you couldn't visually identify, struck German tactical planners as wasteful and impractical. When the first American B-17 seconds appeared over occupied Europe in August 1942, Luftwaffe intelligence officers noted the altitude claims with skepticism. American mission reports stated bombers were operating at 26,000 to 29,000 feet during penetration and bomb runs. German fighter pilots filed after-action reports describing intercepts at 24,000 to 26,000 feet, where their aircraft struggled to reach the bomber formations. The altitude gap was noted, but attributed to measurement error or American exaggeration. Oberst Josef Schmid, Chief of Intelligence for Luftflotte 3, sent a memo to Fighter Command in September 1942, suggesting that actual American bombing altitudes were likely closer to 22,000 feet, with the higher figures representing propaganda meant to demoralize German pilots. Schmid's reasoning was sound based on available data. German intelligence had calculated the service ceiling of the B-17E at approximately 28,000 feet under ideal conditions. But service ceiling meant the maximum altitude where the aircraft could maintain 100 feet per minute climb rate. Nobody operated at service ceiling. You operated 2,000 to 3,000 feet below that for safety margins and maneuverability. Therefore, Schmid concluded, practical operational altitude for B-17 seconds was probably 23,000 to 25,000 feet maximum. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The Americans were rounding up for psychological effect. This assessment filtered through the Luftwaffe's command structure and shaped tactical planning throughout the fall of 1942. Fighter units were told to optimize intercept profiles for targets between 20,000 and 25,000 feet. Anti-aircraft batteries were ranged accordingly, and the urgency to develop specialized high-altitude interceptors was downgraded because the threat seemed manageable with existing equipment. Then, Hauptmann Lang's technical report from the captured B-24 landed on Schmid's desk in early November 1942, and every assumption crumbled. Lang's team at Rechlin had spent 3 weeks analyzing the Liberator's oxygen system. They'd pressure-tested the bottles, disassembled the regulators, examined the delivery masks under laboratory conditions, and calculated the total oxygen capacity against known crew sizes and mission durations. The report's conclusion was unambiguous and disturbing. The B-24's oxygen system was designed and proven capable of sustaining 10 crew members at altitudes up to 30,000 feet for a minimum of 6 hours continuous operation. The system wasn't experimental or theoretical. It was production line equipment, installed on every B-24 coming off American assembly lines. That meant the Americans weren't exaggerating their altitude capability. They were actually operating up there, and they'd engineered entire aircraft around that operational requirement. The technical details in Lang's report read like a catalogue of German engineering inadequacy. The oxygen bottles used seamless steel construction with internal pressure ratings that German manufacturers considered excessive and unnecessary. Each bottle could hold roughly 400 litres of oxygen at 3,000 psi, more than twice the capacity of comparable German equipment. The regulators incorporated automatic pressure compensation. As altitude increased and external air pressure dropped, the regulator automatically increased oxygen flow to maintain proper partial pressure in the pilot's bloodstream. This wasn't something the crew had to think about or manually adjust. The system did it automatically, freeing pilots and bombardiers to focus on navigation and targeting. German oxygen systems required constant manual adjustment. Pilots had to monitor their altitude and manually increase flow as they climbed, a task that was easy to forget when you were also flying formation, watching for fighters, and managing engine parameters. The delivery masks used a pressure-demand design that German aviation medicine specialists had only seen in experimental programs. Instead of providing a constant flow of oxygen that the user breathed from, these masks delivered oxygen under positive pressure, forcing it into the lungs. At extreme altitude, where ambient pressure was minimal, this positive pressure delivery meant the user's lungs were actually being inflated by the oxygen system, ensuring adequate oxygen reached the bloodstream even when normal breathing mechanics were impaired by altitude. Perhaps most impressive was the system's redundancy. The B-24 carried 4 independent oxygen bottles, with cross-feed valves that allowed any bottle to supply any crew station. If one bottle failed or took battle damage, the others could compensate. If a regulator froze, a backup regulator could be selected. If a hose was severed, emergency oxygen connections were available at multiple points throughout the aircraft. The Americans had designed for battle damage and equipment failure at altitude, which meant they expected to regularly operate in conditions where such failures would occur. Lang's report included testimony from interrogated B-24 crew members that filled in operational details. The pilot, a first lieutenant named Raymond Morrison, described routine missions at 28,000 feet, lasting 5 to 6 hours from takeoff to landing. He stated that his bomb group, the 93rd, had standing orders to bomb from minimum altitude of 26,000 feet, with 28,000 preferred for heavily defended targets. The crews called it riding the high step, and Morrison spoke about it the way a truck driver might describe a long highway run. It wasn't heroic or experimental. It was just what they did. The bombardier, Technical Sergeant William Hodge, provided even more concerning intelligence. He described the Norden bomb site's operation at altitude and explained that the site actually worked better above 25,000 feet, where air was thinner and wind effects were more predictable. American bombardiers trained specifically for high-altitude drops. They had altitude correction tables, temperature compensation calculations, and dedicated training facilities back in the United States, where they practiced bomb runs at simulated high altitude. This wasn't a capability the Americans were developing. It was a capability they'd already developed, refined, and deployed operationally. The Luftwaffe was fighting a bomber force that existed in an altitude band where German fighters and flak couldn't effectively reach them, and the Germans hadn't even realized the extent of the problem until they'd captured intact evidence. Schmid forwarded Lang's report to Reichsmarschall Hermann Göring with a cover memo that was remarkably blunt for German military communication. The memo stated that previous intelligence assessments of American bombing altitudes had been incorrect, that American heavy bombers were routinely operating at 27,000 to 29,000 feet, and that current Luftwaffe fighter and flak capabilities were inadequate to counter this threat. The memo recommended immediate priority development of high-altitude interceptors and reassessment of all defensive planning. Göring's response came back within 48 hours, and it wasn't what Schmid expected. Göring questioned whether a single captured bomber was sufficient evidence to overturn established intelligence assessments. He suggested the B-24 question might have been a specially modified reconnaissance variant, not representative of standard bomber equipment. He pointed out that German fighter pilots were regularly engaging American bombers, which wouldn't be possible if the bombers were actually operating beyond fighter ceiling. The response revealed a fundamental problem in German command structure. Göring, despite his World War I flying experience, was now primarily a political figure who didn't want to hear that American industrial capacity had produced a technological advantage the Luftwaffe couldn't match. Accepting Lang's report meant accepting that Germany was behind in a critical area of aerial warfare, and that admission had implications Göring wasn't willing to face. But the evidence kept accumulating. In late November 1942, a B-17F from the 305th Bomb Group was shot down near Bremen after a raid on submarine construction facilities. The bomber had been hit by flak at 27,500 feet, confirmed by multiple radar tracking stations. The wreckage was recovered by Luftwaffe technical teams who found an oxygen system virtually identical to what Lang had documented in the B-24. Same high-pressure bottles, same pressure demand regulators, same automatic compensation systems. In December, another B-24 force landed near Amsterdam with minimal damage, giving German engineers access to an almost complete aircraft. This one was from the 44th Bomb Group, and it carried full documentation including maintenance logs that showed the oxygen system's service history. The logs recorded pre-flight oxygen pressure checks for every mission going back 6 weeks. Every entry showed missions at altitudes above 25,000 feet, some as high as 29,500. These weren't exceptions or special missions. This was routine operational tempo. The interrogation reports from captured American aircrews created their own body of evidence. By January 1943, the Luftwaffe had interrogated roughly 80 American bomber crew members from various groups and squadrons. Interview protocols included detailed questions about operational altitudes. 73 of the 80 prisoners stated without hesitation that their standard bombing altitude was 26,000 to 29,000 feet. They described it matter-of-factly, the way you'd describe standard operating procedure for anything. When German interrogators pressed for details about oxygen usage, the Americans looked confused. Why was this interesting? Everyone used oxygen above 10,000 feet. The regulators were automatic. You plugged in your mask at startup, breathed normally, and the system handled everything else. Some crews mentioned that they'd sleep during long transits to the target, with the oxygen system keeping them alive while they dozed at 28,000 feet. It was so routine that they literally slept through it. This casual competence was perhaps more disturbing to German intelligence than the technical specifications. The Americans hadn't just solved the high-altitude problem. They'd made it mundane. They'd taken something that German aviation medicine considered extremely difficult and turned it into something so reliable that bomber crews didn't even think about it. That level of engineering maturity and operational confidence suggested industrial and technical capabilities that were deeply concerning. By February 1943, enough evidence had accumulated that even Göring couldn't dismiss it. Multiple captured aircraft, dozens of prisoner interrogations, radar tracking data from German air defense networks, and gun camera footage from Luftwaffe fighters all pointed to the same conclusion. American heavy bombers were routinely operating at altitudes between 26,000 and 29,000 feet. They could sustain those altitudes for the entire mission duration, and their crews were doing this day after day without apparent difficulty. The Luftwaffe's Fighter Command conducted a comprehensive analysis of intercept effectiveness against high-altitude bomber formations. The results were grim. The standard Messerschmitt Bf 109G, the backbone of German fighter defense, had a service ceiling of 39,000 feet on paper. In practice, combat operations above 26,000 feet were extremely difficult. At 28,000 feet, the 109G's climb rate dropped to roughly 300 feet per minute. Its turn radius increased dramatically as thin air reduced control surface effectiveness, and combat power was limited to 5 to 10 minutes before engine temperatures climbed into dangerous ranges. Against bomber formations at 28,000 feet, a 109G had to climb for 20 to 25 minutes to reach intercept altitude, conduct perhaps one attack pass, then descend before fuel exhaustion or engine overheat forced withdrawal. The engagement window was maybe 2 minutes of actual combat time for every mission. If the bombers were flying at 29,000 feet, some 109Gs couldn't reach them at all, depending on temperature and load configuration. The Focke-Wulf FW-190, the other primary Luftwaffe interceptor, was even worse at altitude. Its radial engine was optimized for low to medium altitude performance. Above 24,000 feet, the 190 was sluggish and underpowered. Pilots reported that intercepting bombers at 27,000 feet in a 190 felt like trying to swim in mud. You could barely maintain formation, let alone conduct effective attack passes. The flak situation was equally problematic. German 88mm anti-aircraft guns had a maximum effective ceiling of around 26,000 feet under ideal conditions. Against targets at 28,000 feet, the shells were at the absolute edge of their trajectory. Bursts were less dense, less accurate, and less lethal. The Americans had found an altitude sweet spot where they were high enough to reduce flak effectiveness dramatically, but not so high that their bombing accuracy suffered. The full scope of the problem crystallized during a Luftwaffe command conference in early March 1943. Generaloberst Hans Jeschonek, chief of the Luftwaffe General Staff, laid out the intelligence findings and operational data. He stated bluntly that the Americans had achieved a technological advantage in high-altitude operations that the Luftwaffe currently could not match. German fighters were being outperformed not by better pilots or tactics, but by basic engineering. The Americans had simply built their bombers and oxygen systems to work efficiently at altitudes where German equipment struggled. The conference minutes, recovered after the war, show significant debate about how to respond. Some officers argued for immediate crash programs to develop high-altitude interceptors. Others suggested tactical modifications, using slashing attacks from higher altitude or head-on approaches that required less sustained combat time. A few voices suggested that the altitude problem was overblown, that improved pilot training and aggressive tactics could overcome the disadvantage. Jeschonek sided with the technical realists. He authorized priority development of high-altitude interceptor variants, ordered modifications to existing fighters to improve altitude performance, and mandated changes to intercept doctrine that acknowledged the altitude gap. But these were medium-term solutions. The fighters wouldn't be available for months. The tactical changes would help, but couldn't eliminate the fundamental performance gap. In the meantime, American bombers would continue operating at altitudes where the Luftwaffe's ability to stop them was severely compromised. The most immediate response was to oxygen system development. If German fighters were going to fight at 28,000 feet, German pilots needed oxygen equipment that actually worked at that altitude for extended periods. The Luftwaffe's procurement office issued contracts to Dräger, Germany's primary oxygen equipment manufacturer, for advanced pressure demand systems similar to what had been captured from American aircraft. Draeger's engineers examined the American components and immediately identified manufacturing challenges. The American regulators used precision-machined brass and stainless steel components with tolerances measured in thousandths of an inch. German manufacturing was perfectly capable of matching these tolerances, but not at scale. The United States was producing these regulators by the thousands, installing them in hundreds of bombers per month. Germany's industrial capacity was already stretched, supporting existing fighter and bomber production. Adding complex oxygen systems to that manufacturing burden meant something else had to give. The material requirements were equally problematic. The high-pressure oxygen bottles required specific steel alloys and welding procedures. The delivery masks needed synthetic rubber compounds that were in short supply due to the naval blockade cutting off natural rubber imports. The automatic pressure compensation mechanisms required small electrical motors and pressure sensors that drew on manufacturing capacity needed for radar and communications equipment. Germany could build advanced oxygen systems. What Germany couldn't do was build them in sufficient quantities while simultaneously maintaining aircraft production, tank production, U-boat construction, and everything else required to fight a multi-front war. The Americans had the industrial base to do both. They were producing advanced bombers, with advanced oxygen systems, with advanced everything, all at a scale that German planners found difficult to comprehend. Captured American aircrew sometimes provided unintentional intelligence about this industrial disparity. One B-17 co-pilot, when asked about the oxygen system in his bomber, mentioned that it had been replaced completely during a depot maintenance cycle because routine inspection found minor corrosion in one regulator. The Germans pressed for details. The entire system? All bottles? All regulators? All hoses? Yes, the pilot confirmed. Depot maintenance had standing procedures. If any oxygen component showed degradation, they replaced everything as a set. Took about 4 hours. Parts were standard across all B-17 seconds and B-24 seconds, so the depot just pulled replacement units from stock. The German interrogators understood the implications. The Americans had such abundant production capacity that they could afford to replace entire functional systems as preventive maintenance. German fighters often flew with patched oxygen hoses and rebuilt regulators because replacement parts were scarce. The contrast in logistics and industrial capacity was stark. The first production run of improved German oxygen equipment reached operational fighter units in May 1943. Jagdgeschwader 11, based at Husum, received priority delivery of 40 sets of the new pressure demand regulators manufactured by Draeger. The equipment was supposed to enable sustained combat operations at 28,000 feet, matching American bomber altitudes. Pilots conducted test flights to evaluate the new systems. Oberleutnant Wilhelm Jonen, a night fighter pilot temporarily assigned to day operations, filed a report after testing the equipment at altitude. He described the system as functional but problematic. The regulator worked as designed, automatically adjusting oxygen flow based on altitude. But the delivery mask didn't seal properly around his face when he turned his head sharply during simulated combat maneuvers. The positive pressure delivery that was supposed to force oxygen into his lungs created uncomfortable pressure points that became painful after 30 minutes. And most critically, the entire system added roughly 12 pounds of equipment that the pilot had to wear and manage, including the walk-around oxygen bottle needed for ground operations and emergency bailout. Jonen noted that American bomber crews had dedicated positions. The pilot flew, the bombardier aimed, the navigator navigated. Each could focus on their oxygen equipment without compromising their primary duties. A German fighter pilot had to do everything simultaneously: fly the aircraft, navigate, watch for threats, manage engine parameters, coordinate with the formation, and now also monitor and adjust an oxygen system that required constant attention. The cognitive load was significant, and in combat situations where split-second decisions mattered, dealing with oxygen equipment became another task competing for mental bandwidth. Other pilots reported similar experiences. The equipment worked, but it wasn't seamless the way American systems apparently were. Lieutenant Franz Stigler from Jagdgeschwader 27 described his first high-altitude intercept using the new oxygen system in June 1943. His unit engaged a formation of B-17 seconds at 27,500 feet near Wilhelmshaven. Stigler climbed to intercept altitude and immediately felt the effects of extreme cold. The outside air temperature was -48 degrees Fahrenheit. His oxygen mask froze where exhaled moisture condensed on the rubber. Ice formed inside the delivery hose, partially restricting flow. He managed one attack pass, fired perhaps 3 seconds worth of ammunition, and then had to break off because his engine was overheating from the extended high-altitude climb. By the time he descended to 20,000 feet, where engine temperatures normalized, the bomber formation was already 20 miles ahead and climbing. The engagement had lasted less than 4 minutes from initial contact to forced withdrawal. The Americans had been up there for 3 hours already and would remain at altitude for another 2 hours on their return flight. The Luftwaffe's tactical adaptation to the altitude problem evolved through trial and error across 1943. Fighter units developed specialized high-altitude intercept procedures that acknowledged the performance limitations. The standard doctrine became slash attacks from above. Fighters would climb to 30,000 or 31,000 feet, higher than the bomber formations, then dive through the formations at high speed, fire during the brief window when they had favorable geometry, and extend away in a shallow dive that preserved energy. These slash attacks minimized the time spent at extreme altitude where German fighters performed poorly, but they also limited the number of attack passes each fighter could make. After diving through the formation, a fighter needed to climb back to altitude for another pass, which took 10 to 15 minutes. In that time, the bomber formation continued toward its target. A typical intercept might allow 2 or 3 attack passes per fighter before fuel exhaustion forced return to base. Compare that to mid-altitude intercepts, where fighters could orbit with the bombers and conduct sustained attacks. The effectiveness data showed the impact. Luftwaffe kill ratios against American heavy bombers varied significantly with altitude. At 22,000 feet, German fighters averaged 1 bomber destroyed per 8 fighter sorties. At 28,000 feet, that ratio dropped to 1 bomber destroyed per 23 fighter sorties. The Americans were paying attention to these statistics too. Their mission planners explicitly factored altitude into survival calculations. Higher altitude meant fewer losses to both fighters and flak, even if it meant reduced bombing accuracy and increased crew fatigue. By summer 1943, the altitude arms race was evident in mission planning on both sides. American bomber groups received standing orders to maintain minimum altitudes above 26,000 feet for penetration and bomb runs. German fighter controllers positioned intercept formations at 30,000 to 32,000 feet, trading climb time for the altitude advantage needed to conduct diving attacks. And both sides were pushing their equipment and crews to the edge of performance envelopes. The human cost of high-altitude operations manifested differently for each side. American bomber crews dealt with cold, fatigue, and the constant low-grade hypoxia that came from spending 6 to 8 hours at extreme altitude, even with supplemental oxygen. Frostbite was common. Crews would return from missions with blackened fingers and toes, where circulation had been restricted by cold. The psychological impact of being unable to see or hear attackers until they were firing was significant. At 28,000 feet, vision was limited by the thin atmosphere and bright sunlight. You couldn't hear engines over your own aircraft noise. German fighters would appear as dark shapes, fire for a few seconds, and disappear before defensive gunners could respond effectively. German fighter pilots faced different pressures. The extended climbs to intercept altitude were exhausting. A pilot might spend 40 minutes climbing, fighting the aircraft's sluggish controls and struggling with oxygen equipment, only to get one brief firing pass before having to descend. The cold was worse for German pilots because fighter cockpits had minimal insulation compared to bomber crew stations. Some pilots reported that their fingers were so numb after high-altitude combat that they couldn't manipulate the landing gear controls during landing approach. They had to descend slowly, warming up at lower altitude before attempting to land. The medical data from both sides tells its own story. The USAAF Medical Corps conducted studies on bomber crews throughout 1943, documenting the physiological effects of repeated high-altitude missions. They found that crews flying regular missions at 28,000 feet experienced cumulative fatigue that standard rest periods didn't fully resolve. Symptoms included persistent headaches, difficulty concentrating, disrupted sleep patterns, and increased susceptibility to respiratory infections. The studies recommended rotating crews off high-altitude duty every 6 to 8 missions for extended rest periods. The Luftwaffe Medical Service conducted similar studies with fighter pilots conducting high-altitude intercepts. Their findings were more severe. German pilots showed signs of chronic hypoxia, even with oxygen supplementation, attributed to the inadequate oxygen systems and the stress of combat operations at altitude. Several pilots were grounded after developing symptoms consistent with altitude sickness, unusual for people who weren't mountain climbers, but explicable given the repeated exposure to extreme conditions. One Luftwaffe medical officer, Stabsarzt Heinrich Becker, wrote in a report from August 1943 that he was observing concerning patterns in pilots assigned to high-altitude intercept duties. They showed elevated rates of disorientation, poor judgment during debriefing, and what he termed cognitive degradation. Becker theorized that the combination of inadequate oxygen, extreme cold, and combat stress at altitude was causing subtle brain damage that accumulated over multiple missions. He recommended limiting pilots to no more than 4 high-altitude intercepts per week, with mandatory rest periods between missions. The recommendation was filed and ignored. The Luftwaffe didn't have enough pilots to implement such restrictions. If a pilot was physically capable of flying, he flew. The long-term health effects were secondary to the immediate operational necessity of putting fighters in the air against incoming bomber formations. The technological gap that started with oxygen systems extended into every aspect of high-altitude operations. American bombers had heated flight suits, electrically warmed gloves and boots powered by the aircraft's electrical system. German pilots had heavy leather jackets and multiple layers of wool clothing that restricted movement and added weight. American crews had relief tubes plumbed into the aircraft's waste system, allowing crew members to urinate without leaving their stations during 8-hour missions. German pilots used relief bottles or simply held it, with predictable effects on comfort and concentration during extended flights. These seem like minor details, but they accumulated into significant operational advantages. An American bombardier could spend 30 minutes making fine adjustments to his bomb sight while staying warm and relatively comfortable at 28,000 feet. A German fighter pilot spending 30 minutes at that altitude was fighting cold, managing inadequate oxygen equipment, and dealing with physical discomfort that degraded his combat effectiveness. The side that had solved the mundane problems of high-altitude flight had more mental and physical resources available for the actual combat mission. The intelligence picture that Hauptmann Lang had begun to assemble in October 1942 became clearer and more disturbing throughout 1943. Each captured bomber added data points. Each interrogated crew member provided operational details. The pattern that emerged showed American strategic planning operating on a timescale and industrial scale that Germany couldn't match. The oxygen systems weren't improvised solutions or experimental equipment rushed into service. They were mature technology that had been developed, tested, and refined before the war started. The United States Army Air Corps had been researching high-altitude operations since the mid-1930s. They'd built altitude chambers, conducted physiological studies, and developed specialized equipment specifically for stratospheric flight. By the time America entered the war, they had production-line oxygen systems that were more advanced than anything Germany had in experimental programs. This pattern repeated across multiple systems. American bombers had turbocharged engines that maintained power output at altitude. German bombers used superchargers that were less effective above 20,000 feet. American aircraft had sophisticated heating systems for guns and equipment to prevent freezing at altitude. German systems were simpler and prone to failure in extreme cold. American crews trained extensively in altitude chambers, where they experienced simulated high-altitude conditions and learned to recognize hypoxia symptoms. German pilot training included basic oxygen instruction, but nothing approaching the comprehensive preparation American crews received. The cumulative effect was that the Americans had built an entire operational ecosystem around high-altitude strategic bombing. They hadn't just solved one problem. They'd solved dozens of interconnected problems, from oxygen delivery to cold weather equipment to specialized navigation systems to crew training protocols. And they'd done all of this before their bombers ever reached European skies. Captured documents from American bomber groups provided additional evidence of this systematic approach. When a B-17 from the 91st Bomb Group was shot down near Regensburg in August 1943, German intelligence recovered the aircraft's crew station cards, laminated checklists that each crew member used during missions. The oxygen system checklist alone was 32 items long, covering pre-flight checks, in-flight, monitoring, emergency procedures, and post-flight documentation. The Americans had broken down high-altitude oxygen management into detailed procedures that left nothing to chance. Compare this to German fighter procedures, where oxygen instruction was essentially plug in your mask and breathe. The American systematic approach reflected industrial thinking applied to military operations. If you could reduce a complex task to a checklist and train people to follow that checklist reliably, you could achieve consistent results at scale. The Luftwaffe relied more on individual pilot skill and experience, which worked well for elite units but didn't scale effectively across an expanding force. By late 1943, the strategic implications were clear to senior Luftwaffe leadership, even if public statements couldn't acknowledge the problem. The Americans had seized an operational advantage in the vertical dimension of air warfare. They could bomb from altitudes where German defenses were significantly degraded. This meant higher bomber survival rates, which meant more bombers reaching their targets, which meant more damage to German industrial capacity. The oxygen systems that Hauptmann Lang had examined in that French field weren't just interesting technology. They were a key enabling capability for the entire American strategic bombing campaign. The Luftwaffe's response evolved throughout late 1943 and into 1944, but it was always reactive, always trying to counter an advantage the Americans had already established. New fighter variants appeared with improved high-altitude performance. The Messerschmitt Bf-109G6 featured a pressurized cockpit that maintained sea-level atmospheric pressure up to 40,000 feet, eliminating the need for oxygen systems entirely. But production was limited, perhaps 300 aircraft total by mid-1944, not enough to make a strategic difference. Tactical innovations helped at the margins. Luftwaffe controllers began positioning fighter formations at extreme altitude, sometimes 35,000 feet, to gain the energy advantage for diving attacks. They coordinated multiple fighter groups to hit bomber formations from different altitudes simultaneously, forcing the Americans to defend against threats from above and below. These tactics increased kill ratios somewhat, but they also increased fuel consumption and reduced the number of attack passes each fighter could make. The flak forces adapted too. New anti-aircraft guns entered service with better high-altitude performance. The 105mm Flak 42 had an effective ceiling of 31,000 feet, finally able to reach American bomber altitudes. But producing and deploying these weapons took time, and the Americans were already operating at those altitudes. The Germans were always catching up, never getting ahead. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The broader impact on the air war became quantifiable by early 1944. The 8th Air Force's loss rates per sortie declined from approximately 6% in mid-1943 to roughly 3% by March 1944. Multiple factors contributed to this improvement. long-range fighter escorts, better tactics, increased bomber armament. But altitude was a significant component. Missions flown at 28,000 feet experienced roughly half the losses of comparable missions at 22,000 feet. The German armaments industry felt the effects directly. Bombing accuracy from 28,000 feet was lower than from medium altitude, but the sheer volume of bombs being dropped compensated. American bombers that previously might have been shot down before reaching their targets were now completing their missions and returning to England. The cumulative tonnage of bombs hitting German factories, rail yards, and oil refineries increased month over month throughout 1944. German production statistics show the impact. Ball-bearing production, concentrated in factories at Schweinfurt and elsewhere, became a primary American target. Despite massive defensive efforts, including permanently stationed fighter units and concentrated flak belts, American bombers repeatedly hit these facilities from high altitude. Ball-bearing production dropped from 8 million units per month in mid-1943 to approximately 4 million per month by summer 1944. The Americans weren't achieving precision bombing in the way pre-war doctrine envisioned, but they were achieving strategic effect through volume and persistence. The oxygen system analysis that began with Hauptmann Lang examining a crashed B-24 had revealed something more significant than just technology. It had exposed a fundamental difference in how each side approached the industrial warfare problem. The Americans had correctly identified high-altitude operations as a valuable capability, invested years in developing the necessary technology, built that technology at industrial scale, and deployed it systematically across their bomber force. The Germans had also understood that high altitude offered advantages, but they hadn't committed the resources to exploit it. Part of this was doctrine. The Luftwaffe was designed around tactical air support for ground operations, not independent strategic bombing. Part of it was resources. Germany's industrial base was smaller and already stressed by multi-front war commitments, but part of it was also strategic vision. The Americans had looked at the bomber war problem and concluded that altitude advantage was worth significant investment. The Germans had looked at the same problem and concluded that other priorities mattered more. By 1944, that strategic choice was costing Germany heavily. Every mission that American bombers flew at 28,000 feet was a mission where German defensive effectiveness was compromised. Every bomber that survived because it operated above effective fighter and flak altitude was another bomber that would return tomorrow and the next day and the day after that, gradually grinding down German industrial capacity through sheer persistence. The psychological impact on both sides was significant. American bomber crews developed confidence from knowing they held an altitude advantage. They understood they were still in danger, that German fighters could still reach them and flak could still hit them, but the knowledge that their altitude made them harder targets provided measurable morale benefits. Replacement crews arriving in England heard stories about missions flown at extreme altitude, where most bombers returned safely. It gave them hope that survival was possible. German fighter pilots experienced the opposite effect. They knew they were fighting at a disadvantage. They could see American bombers operating in an altitude band where German fighters struggled, and there was nothing individual courage or skill could do to overcome that fundamental performance gap. Some pilots became fatalistic, accepting that high-altitude intercepts were dangerous missions with poor odds. Others became more aggressive, taking risks that sometimes paid off but more often resulted in their own loss. The transformation of the air war over Europe between 1942 and 1944 is often attributed to long-range fighter escorts, particularly the P-51 Mustang's ability to accompany bombers deep into Germany. That was certainly a critical factor. But the altitude advantage that American bombers held, enabled by their sophisticated oxygen systems and high-altitude engineering, was equally important and less recognized. The Mustangs protected bombers from fighter attack. The altitude protected them from both fighters and flak, and it did so for every minute of every mission. Hauptmann Lang continued analyzing captured American equipment throughout 1944, though by then the focus had shifted from understanding capabilities to trying to copy them. His reports became increasingly technical, less about what the Americans could do, and more about how German industry might replicate specific components. But the underlying reality never changed. The Americans had gotten there first, built the infrastructure to exploit their advantage, and were operating at a scale Germany couldn't match. One of Lang's last reports from late 1944 addressed a B-17G that had been forced down near Munich with minimal damage. This aircraft had the latest oxygen system refinements, including improved regulators, better cold weather performance, and enhanced redundancy. Lang's technical team spent weeks analyzing every component. The report concluded with a paragraph that summarized the entire oxygen system story. The enemy has achieved systematic engineering superiority in high-altitude operations. Individual components can be replicated with German manufacturing, but the integrated system performance and production scale cannot be matched with available resources. The operational advantage this provides to enemy bombing operations is decisive and unlikely to be overcome through defensive measures. That clinical assessment, buried in a technical report that probably reached a handful of senior officers, was as close as anyone in the Luftwaffe came to officially acknowledging what the evidence had shown since October 1942. The Americans had won the altitude war before most people realized there was an altitude war to fight. The bomber crews who flew those missions at 28,000 feet, breathing through oxygen masks connected to pressure demand regulators, probably didn't think much about the technology keeping them alive. It was just part of the mission routine. Plug in your oxygen, check the flow, adjust your heated suit, and focus on the target. The engineering that made all of that possible was invisible to them, working automatically in the background. But that invisible engineering was winning the war in ways that bombing accuracy and firepower alone couldn't. It was putting American bombers in an operational space where German defenses were less effective. It was bringing crews home who might otherwise have been shot down. It was allowing the strategic bombing campaign to persist and intensify despite determined German resistance. And it had all started with oxygen bottles and regulators, the mundane technology that no one thought about until German intelligence officers examined a crashed bomber and realized what they were actually fighting against. The story of high-altitude operations in World War II is often told as a story of aircraft performance, bomb tonnages, and kill ratios. Those are important metrics. But underneath all of them is a story about engineering decisions made years before the first bomb fell. About American planners who looked at the problem of strategic bombing and decided that reliable high-altitude operations were worth significant investment. About industrial systems that could produce complex equipment at scale, and about the cumulative advantage that comes from solving all the small problems that add up to operational superiority. When Hauptmann Lang stood in that French field in October 1942, examining oxygen hoses and pressure regulators, he was looking at evidence of a war that Germany had already lost in the engineering phase. The battles would continue for 2.5 more years. Tens of thousands more would die on both sides. But the outcome was already visible in those oxygen bottles if you knew what you were looking for. The Americans had built their bombers to own the sky at 28,000 feet, and by the time the Germans fully understood what that meant, it was already too late to catch up. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.